Welcome to Quantum Mechanics. My name is Brant Carlson. Since this is the first lecture on quantum mechanics, we ought to have some sort of an introduction. And what I want to do to introduce quantum mechanics is to explain, first of all, why it's necessary, and second of all, to put it in historical context to, I'll show one of the most famous photographs in all of physics that really gives you a feel for the brain power that went into the construction of this theory. And hopefully we'll put it in some historical context as well, so you can understand where it fits in the broader philosophy of science. But the main goal of this lecture is about the need for quantum mechanics, which I really ought to just have called, Why Do We Need Quantum Mechanics? This subject has a reputation for being a little bit annoying, so why do we bother with it? Well, first off, for some historical context, imagine yourself back in 1900. Turn of the century, science has really advanced a lot. We have electricity, we have all this fabulous stuff that electricity can do, and even almost 100 years before that, physicists thought they had things figured out. There's a famous quote from Laplace, "Given for one instant an intelligence which could comprehend all the forces by which nature is animated, and the respective position of the beings which compose it, nothing would be uncertain, and the future, as the past, would be present to its eyes." Now, maybe you think intelligence which can comprehend all the forces of nature is a bit of a stretch. And maybe such a being which can know all the respective positions of everything in the universe is a bit of a stretch as well. But the feeling at the time was that if you could do that, you would know everything. If you had perfect knowledge of the present, you could predict the future. And of course you can infer what happened in the past. And everything is connected by one unbroken chain of causality. Now, in 1903, Albert Michelson, another famous quote from that time period, said, "The more important fundamental laws and facts of physical science have all been discovered. Our future discoveries must be looked for in the sixth place of decimals." Now, this sounds rather audacious. This is 1903, and he thought that the only thing that we had left to nail down was the part in a million level precision. Well, to be fair to him, he wasn't talking about never discovering new fundamental laws of physics. He was talking about really astonishing discoveries like the discovery of Uranus on the basis of orbital perturbations of Neptune. Never having seen the planet Uranus before, they figured out that it had to exist just by looking at things that they had seen. That's pretty impressive. And Michelson was really onto something. Precision measurements are really, really useful, especially today. But back in 1903, it wasn't quite so simple, and Michelson probably regretted that remark for the rest of his life. The attitude that I want you guys to take when you approach quantum mechanics, though, is not this sort of 1900s notion that everything is predicted. It comes from Shakespeare. Horatio says, "One, oh day and night, but this is wondrous strange," to which Hamlet replies, one of the most famous lines in all of Shakespeare, "And therefore as a stranger give it welcome. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." So that's the attitude I want you guys to take when you approach quantum mechanics. It is wondrous strange, and we should give it welcome. There are some things in quantum mechanics that are deeply non-intuitive, but if you approach them with an open mind, quantum mechanics is a fascinating subject, and there's a lot of really fun stuff that goes on. Now, to move on to the necessity for quantum mechanics, there were some dark clouds on the horizon, even at the early 20th century. Michelson wasn't quite having a big enough picture in his mind when he said that everything was down to the sixth place of decimals. The dark clouds on the horizon, at least according to Kelvin here, were a couple of unexplainable experiments. One, the black body spectrum. Now, a black body you can just think of as a hot object. And a hot object, like, for example, the coils on an electrical stove, when they get hot, will glow. And the question is, what color do they glow? Do they glow red? Do they glow blue? What is the distribution of radiation that is emitted by a hot object? Another difficult to explain experiment is the photoelectric effect. If you have some light and it strikes a material, electrons will be ejected from the surface. And as we'll discuss in a minute, the properties of this experiment do not fit what we think we know about, or at least what physicists thought they knew about the physics of light and the physics of electrons at the turn of the 20th century. The final difficult experiment to explain is bright line spectra. For example, if I have a flame coming from, say, a Bunsen burner, and I put a chunk of something, perhaps sodium, in that flame, it will emit a very particular set of frequencies that looks absolutely nothing like a black body. We'll talk about all of these experiments in general, or in a little bit more detail in a minute or two, but just looking at these experiments now, these are all experiments that are very difficult to explain, knowing what we knew at the turn of the 20th century about classical physics. And there are also experiments that involve light and matter. So we're really getting down to the details of what stuff is really made of and how it interacts with the things around it. These are some pretty fundamental notions, and that's where quantum mechanics really got its start. So let's pick apart these experiments in a little more detail. The black-body spectrum, as I mentioned, you can think of as the light that's emitted just by a hot object. And while hot objects have some temperature associated with them, let's call that T. The plot here on the right is showing very qualitatively, I'll just call it the intensity of the light emitted as a function of the wavelength of that light. So short wavelengths, high energy, long wavelengths, low energy. Now if you look at T equals 3500 Kelvin curve here, it has a long tail to long wavelengths, and it cuts off pretty quickly as you go to short wavelengths. So it doesn't emit very much high energy light. Whereas if you have a much hotter object, 5500 Kelvin, it emits a lot more high energy light. The red curve here is much higher than the black curve. Now if you try to explain this, knowing what early 20th century physicists knew about radiation and about electrons and about atoms and how they could possibly emit light, you get a prediction. And it works wonderfully well up until about here, at which point it blows up to infinity. Infinities are bad in physics. This is the Rayleigh-Jeans law, and it works wonderfully well for long wavelengths, but does not work at all for short wavelengths. That's called the ultraviolet catastrophe, if you've heard that term. On the other end of things, if you look at what happens down here, well, it's not so much a prediction but an observation, but there's a nice formula that fits here. So on one side we have a prediction that works well on one end but doesn't work on the other. And on the other hand we have a sort of empirical formula called Wien's law that works really well at the short wavelengths, but, well, also blows up to infinity at the long wavelengths. Both of these blowing up things are a problem. And the question is, how do you get something that explains both of them? This is the essence of the black-body spectrum and how it was difficult to interpret in the context of classical physics. The next experiment I mentioned is the photoelectric effect. This is sort of the opposite problem. It's not how a material emits light, it's how light interacts with the material. So you have light coming in, and the experiment is usually done like this. You have your chunk of material, typically a metal, and when light hits it, electrons are ejected from the surface, hence the electric part of the photoelectric effect. And you do all this in a vacuum, and the electrons are then allowed to go across a gap to some other material, another chunk of metal, where they strike this metal. And the experiment is usually done like this. You connect it up to a battery. So you have your material on one side and your material on the other, and you have light hitting one of these materials and ejecting electrons. And you tune the voltage on this battery such that your electrons, when they're ejected, never quite make it. So the electric field produced by this voltage is opposing the motion of the electrons. When that voltage is just high enough to stop the motion of the electrons, keep them from completely making it all the way across, we'll call that the stopping voltage. Now, it turns out that what classical E&M predicts, as I mentioned, doesn't match what actually happens in reality. But let's think about what does classical E&M predict here. Well, classical electricity and magnetism says that electromagnetic waves here have electric fields and magnetic fields associated with them, and these are propagating waves. If I increase the intensity of the electromagnetic wave, that means the magnitude of the electric field involved in the electromagnetic wave is going to increase. And if I'm an electron sitting in that electric field, the energy I acquire is going to increase. That means V stop is going to increase, because I'll have to have more voltage to stop a higher energy electron, as would be produced by a higher intensity beam of light. The other parameter of this incoming light is its frequency. So we can think about varying the frequency. If I increase the frequency, I have more intense light. Now, that doesn't say anything about the string, if I increase the frequency, I don't necessarily have more intense light. The electric field magnitude is going to be the same, which means the energy and the stopping voltage will also be the same. Now, it turns out what actually happens in reality does not match this at all. In reality, when the intensity increases, the energy, which I should really write as V stop, the stopping voltage necessary, doesn't change. And when I increase the frequency, the voltage necessary to stop those electrons increases. So this is sort of exactly the opposite. What's going on here? That's the puzzle in explaining the photoelectric effect. Just to briefly check your understanding, consider these plots of stopping voltage as a function of the parameters of the incident light, and check off which you think shows the classical prediction for the photoelectric effect. The third experiment that I mentioned is bright line spectra. And as I mentioned, this is what happens if you take a flame or some other means of heating a material, like the bar of sodium I mentioned earlier. This will emit light, and in this case, the spectrum of light from red to blue of sodium looks like this. Actually, I'm sorry, that's not sodium, that's mercury. These are four different elements: hydrogen, mercury, neon, and xenon. And instead of getting a broad, continuous distribution, like you would from a black body, under these circumstances where you're talking about gases, you get these very bright regions. It's the spectrum, instead of looking like a smooth curve like this, looks like spikes. Those bright lines are extraordinarily difficult to explain with classical physics, and this is really the straw that broke the camel's back, broke classical physics' back, that really kicked off quantum mechanics. How do you explain this? This is that famous photograph that I mentioned. This is really the group of people who first built quantum mechanics. Now, I mentioned three key experiments. The black body spectrum. This guy figured that out. This is Planck. The photoelectric effect. This guy, who I hope needs no introduction, this is Einstein, figured that out. This is the paper that won Einstein the Nobel Prize. And as far as the bright line spectra of atoms, it took a much longer time to figure out how all of that fit together. And it took a much larger group of people. But they all happen to be present in this photograph. There's this guy, and this guy, and these two guys, and this guy. This photograph is famous because these guys worked out quantum mechanics. But that's not the only, these aren't the only famous people in this photograph. You know this lady as well. This is Marie Curie. This is Lorentz, which if you studied special relativity, you know Einstein used the Lorentz transformations. Pretty much everyone in this photograph is a name that you know. I went through and looked up who these people were, these were all of the names that I recognized, which doesn't mean that the people whose names I didn't recognize weren't also excellent scientists. For example, C.T.R. Wilson here, one of my personal favorites, inventor of the cloud chamber. This is the brain trust that gave birth to quantum mechanics, and it was quite a brain trust. You had some of the most brilliant minds of the century working on some of the most difficult problems of the century. And what's astonishing is they didn't really like what they found. They discovered explanations that made astonishingly accurate predictions, but throughout the history you keep seeing them disagreeing, like, no, that can't possibly be right. Not necessarily because the predictions were wrong or they thought there was a mistake somewhere, but because they just disliked the nature of what they were doing. They were upending their view of reality. Einstein, in particular, really disliked quantum mechanics to the day that he died, just because it was so counterintuitive. And so with that introduction to a counterintuitive subject, I'd like to remind you again of that Shakespeare quote, "There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." Try to keep an open mind, and hopefully we'll have some fun at this. Knowing that quantum mechanics has something to do with explaining the interactions of light and matter, for instance, in the context of the photoelectric effect, or black body radiation, or bright line spectra of atoms and molecules, one might be led to the question of when is quantum mechanics actually relevant? The domain of quantum mechanics is unfortunately not a particularly simple question. When does it apply? Well, on the one hand, you have classical physics, and on the other hand, you have quantum physics. And the boundary between them is not really all that clear. On the classical side, you have things that are certain, whereas on the quantum side, you have things that are uncertain. What that means in the context of physics is that on the classical side, things are predictable. They may be chaotic and difficult to predict, but in principle they can be predicted. Well, on the quantum side, things are predictable too, but with a caveat. In the classical side, you determine everything. Basically, every property of the system can be known with perfect precision, whereas in quantum mechanics, what you predict are probabilities. And learning to work with probabilities is going to be the first step to getting comfortable with quantum mechanics. The boundary between these two realms, when the uncertain and probabilistic effects of quantum mechanics start to become relevant, is really a dividing line between things that are large and things that are small. And that's not a particularly precise way of stating things. Doing things more mathematically, quantum mechanics applies, for instance, when angular momentum L is on the scale of Planck's constant, or the reduced Planck's constant, h bar. Now, h bar is the fundamental scale of quantum mechanics, and it appears not only in the context of angular momentum. Planck's constant has units of angular momentum, so if your angular momentum is of order Planck's constant or smaller, you're in the domain of quantum mechanics. We'll learn more about uncertainty principles later as well, but uncertainties in this context have to do with products of uncertainties. For instance, the uncertainty in the momentum of a particle times the uncertainty in the position of the particle. This, if it's comparable to Planck's constant, is also going to give you the realm of quantum mechanics. Energy and time also have an uncertainty relation, again, approximately equal to Planck's constant. Most fundamentally, the classical action, when you get into more advanced studies of classical mechanics, you'll learn about a quantity called the action, which has to do with the path a system takes as it evolves in space and time. If the action of the system is of order Planck's constant, then you're in the quantum mechanical domain. Now, Planck's constant is a really small number. It's 1.05 times 10 to the negative 34 kilogram meters squared per second. times 10 to the negative 34 is a small number. So if we have really small numbers, then we're in the domain of quantum mechanics. In practice, these guys are the most useful, whereas this is the most fundamental. But we're more interested in useful things than we are in fundamental things, after all. For example, the electron in the hydrogen atom. Now, you know from looking at the bright line spectra that this should be in the domain of quantum mechanics. But how can we tell? Well, to use one of the uncertainty principles as a calculation, consider the energy. The energy of an electron in a hydrogen atom is, let's say about 10 electron volts. If we say that's p squared over 2m, using the classical kinetic energy relation between momentum and kinetic energy, that tells us that the momentum, p, is going to be about 1.7 times 10 to the minus 24th kilogram meters, kilogram, where'd it go? Where's my eraser? Kilogram meters per second. Now, this suggests that the momentum of the electron is, non-zero. But if a hydrogen atom itself is not moving, we know the average momentum of the electron is 0. So if the momentum of the electron is going to be 0 with still some momentum being given to the electron, this is more the uncertainty in the electron momentum than the electron momentum itself. The next quantity, if we're looking at the uncertainty relation between momentum and position, is we need to know the size of, or the uncertainty in the position of the electron, which has to do with the size of the atom. Now, the size of the atom, that's about 0.1 nanometers, which, if you don't remember the conversion from nanometers, is 10 to the minus 10th meters. So let's treat this as delta x, our uncertainty in position, because we don't really know where the electron is within the atom, so this is a reasonable guess at the uncertainty. Now, if we calculate these two things together, delta p, delta x, you get something, I should say this is approximate because this is very approximate, 1.7 times 10 to the negative 34th, and if you plug through the units, it's kilogram meter squared per second. This is about equal to h bar. So this tells us that quantum mechanics is definitely important here. We have to do some quantum in order to understand this system. As an example of another small object that might have quantum mechanics relevant to it, this is one that we would actually have to do a calculation. I don't know intuitively whether a speck of dust in a light breeze is in the realm of quantum mechanics or classical physics. Now, I went online and looked up some numbers. For a speck of dust, let's say the mass is about 10 to the minus 6th kilograms, a microgram. It has a velocity in this light breeze of, let's say, 1 meter per second. And make myself some more space here. The size of this speck of dust is going to be about 10 to the minus 5 meters. So these are the basic parameters of this speck of dust in a light breeze. Now we can do some calculations with this. For instance, momentum. Well, in order to understand quantum mechanics, there's some basic vocabulary that I need to go over. So let's talk about the key concepts in quantum mechanics. Thankfully, there are only a few. There's really only 3, and the first is the wave function. The wave function is, and always has been, written as psi, the Greek letter. My handwriting gets a little lazy sometimes, and it'll end up just looking like this, but technically, it's supposed to look something like that. Details are important, provided you recognize the symbol. Psi is a function of position, potentially in 3 dimensions, x, y, and z, and time. And the key facts here is that psi is a complex function, which means that while x, y, z, and t here are real numbers, psi, evaluated at a particular point in space, will potentially be a complex number with both a real and imaginary part. What is subtle about the wave function, and we'll talk about this in great detail later, is that while it represents the state of the system, it doesn't tell you with any certainty what the observable properties of the system are. It really only gives you probabilities. So for instance, if I have a coordinate system, something like this, where say this is position in the x direction, psi, with both real and imaginary parts, might look something like this. This could be the real part of psi, and this could be, say, the complex or the imaginary part of psi. What is physically meaningful is the squared magnitude of psi, which might look something like this in this particular case. And that is related to the probability of finding the particle at a particular point in space. As I said, we'll talk about this later, but the key facts that you need to know about the wave function is that it's complex and it describes the state of the system, but not with certainty. The next key concept in quantum mechanics is that of an operator. Now, operators are what connect psi to observable quantities. That is one thing operators can do. Just a bit of notation, usually we use hats for operators. For instance, x hat or p hat are operators that you'll encounter shortly. Operators act on psi. So if you want to apply, for instance, the x hat operator to psi, you would write x hat psi. As if this were something that as it appears on the left of psi, the assumption is that x acts on psi. If I write psi x hat, doesn't necessarily mean that x hat acts on psi. You assume operators act on whatever lies to the right. Likewise, of course, p hat psi. Now, we'll talk about this in more detail later, but x hat, the operator, can be thought of as just multiplying by x. So if I have psi as a function of x hat psi is just going to be x times psi of x. So if psi was a polynomial, you could multiply x by that polynomial. The p operator, p hat, as another example, is a little bit more complicated. This is just an example now, and technically this is the momentum operator, but we'll talk more about that later. It's equal to minus h bar times the derivative with respect to x. So this is again something that needs a function, needs the wave function to actually give you anything meaningful. Now the important thing to note about the operators is that they don't give you the observable quantities either. But in quantum mechanics, you can't really say the momentum of the wave function. For instance, p hat psi is not, and I'll put this in quotes because you won't hear this phrase very often, the momentum of psi. It's the momentum operator acting on psi, and that's not the same thing as the momentum of psi. The final key concept in quantum mechanics is the Schrödinger equation. And this is really the big equation. So I'll write it big. I, h bar, partial derivative of psi with respect to time is equal to h hat, that's an operator, acting on psi. Now h hat here is the Hamiltonian, which you can think of as the energy operator. So the property of the physical system that H is associated with is the energy of the system. And the energy of the system can be thought of as a kinetic energy. So we can write a kinetic energy operator plus a potential energy operator together acting on psi. And it turns out the kinetic energy operator can be written down. This is going to end up looking like minus h bar squared over 2m partial derivative of psi with respect to, second partial derivative of psi with respect to position, plus, and then the potential energy operator is going to look like the potential energy as a function of position just multiplied by psi. So this is the Schrodinger equation. Typically, you'll be working with it in this form. So IH bar times the partial derivative with respect to time is related to the partial derivative with respect to space, and then multiplied by some function. The basic quantum mechanics that we're going to learn in this course mostly revolves around solving this function and interpreting the results. So to put these in a bit of a roadmap, we have operators. We have the Schrodinger equation. And we have the wave function. Now operators act on the wave function, and operators are used in the Schrodinger equation. Now the wave function that actually describes the state of the system is going to be the solution to the Schrodinger equation. Now I mentioned operators acting on the wave function. What they give you when they act on the wave function is some property of the system, some observable perhaps. And the other key fact that I mentioned so far is that the wave function doesn't describe the system perfectly, it only gives you probabilities. So that's our overall concept map. To put this in the context of the course outline, the probabilities are really the key feature of quantum mechanics, and we're going to start this course with a discussion of probabilities. We'll talk about the wave function after that and how the wave function is related to those probabilities, and we'll end up talking about operators and how those operators and the wave functions together give you probabilities associated with observable quantities. That will lead us into a discussion of the Schrodinger equation, which will be most of the course, really. The bulk of the material before the first exam will be concerned with various examples. Solution to the Schrodinger equation under various circumstances. This is really the main meat of quantum mechanics in the beginning. After that, we'll do some formalism. And what that means is we'll learn about some advanced mathematical tools that make keeping track of all the details of how all of this fits together a lot more straightforward. And then we'll finish up the course by doing some applications. So those are our key concepts and a general roadmap through the course. Hopefully now you have the basic vocabulary necessary to understand phrases like the momentum operator acts on the wave function, or the solution to the Schrodinger equation describes the state of the system, and that sort of thing. Don't worry too much if these concepts haven't quite clicked. In order to really understand quantum mechanics, you have to get experience with them. These are not things that you really have any intuition for based on anything you've seen in physics so far. So bear with me, and this will all make sense in the end, I promise. Complex numbers, or numbers involving, conceptually you can think about it as the square root of -1, I, are essential to understanding quantum mechanics, since some of the most fundamental concepts in quantum mechanics, for instance the wave function, are expressed in terms of complex numbers. Complex analysis is also one of the most beautiful subjects in all of mathematics, but unfortunately, in this course I don't have the time to go into the details. Lucky you, perhaps. Here's what I think you absolutely need to know to understand quantum mechanics from the perspective of complex analysis. First of all, there's the basic definition. I squared is equal to -1, which you can think of also as I equals the square root of -1. In general, a complex number, z, then, can be written as the sum of a purely real part, x, and a purely imaginary part, I times y. Note in this expression, z is complex, x and y are real, where I times y is purely imaginary. The terms purely real or purely imaginary in the context of this expression like this, x plus iy, something is purely real if y is 0, something is purely imaginary if x is 0. As far as some notation for extracting the real and imaginary parts, typically mathematicians will use this funny calligraphic font to indicate the real part of x plus iy or the imaginary part of x plus iy, and that just pulls out x and y. Note that both of these are real numbers. When you pull out the imaginary part, you get x and y. You don't get iy, for instance. Another one of the most beautiful results in mathematics is e to the I pi plus 1 equals 0. This formula kind of astonished me when I first encountered it, but it is a logical extension of this more general formula that e raised to a purely imaginary power iy is equal to the cosine of y plus I times the sine of y. This can be shown in a variety of ways, in particular involving the Taylor series. If you know the Taylor series for the exponential, the Taylor series for cosine of y, and the Taylor series for sine of y, you can show quite readily that the Taylor series for complex exponential is the Taylor series of cosine plus the Taylor series of sine. And while that might not necessarily constitute a rigorous proof, it's really quite fun if you get the chance to go through it. At any rate, the trigonometric functions here, cosine and sine, should be suggestive, and there is a geometric interpretation of complex numbers that we'll come back to in a minute. But for now, know that while we have rectangular forms like this, x plus iy, where x and y, the nomenclature there is chosen on purpose, you can also express this in terms of r e to the I theta, where you have now a radius and an angle. The angle here, by the way, is going to be the arctangent of y over x. And we'll see why that is in a moment when we talk about the geometric interpretation. But given these rectangular and polar forms of complex numbers, what do the basic operations look like? How do we manipulate these things? Well, addition and subtraction in rectangular form is straightforward. If we have two complex numbers, a plus ib plus, and we want to add to that the second complex number, c plus id, we just add the real parts, a and c, and we add the imaginary parts, b and d. This is just like adding in any other sort of algebraic expression. Multiplication is a little bit more complicated. You have to distribute, and you distribute in the usual sort of draw a smiley face kind of way. A times c and b times d are going to end up together in the real part. And the reason for that is, well, a times c, a and c both being real numbers, a times c will be real. Whereas ib times id, both being purely complex numbers, you'll end up with b times d times I squared, and I squared is minus 1. So you just end up with minus bd, which is what we see here. Otherwise, the complex part is perhaps a little more easy to understand. You have I times d times c, and you have a times I times d, both of which end up with plus signs in the complex part. Division, in this case, is like rationalizing the denominator, except instead of involving radicals, you have complex numbers. If I have some number a plus ib divided by c plus id, I can simplify this by both multiplying and dividing by c minus id. Note the sign change in the denominator here. C plus id is then prompting me to multiply by c minus id over c minus id. Now, when you do the distribution there, for instance, let's just do it in the denominator, c plus id times c minus id, my top eyebrows here of the smiley face, c squared times id, or c squared plus, now, id times minus id, which is, well, I'll just write it out, I times minus id, which is going to be d squared times I times minus I. So I squared times minus 1, and I squared is minus 1. So I have minus 1 times minus 1, which is just 1, so I can ignore that. I just got d squared. So what I end up with in the denominator is just c squared plus d squared. What I end up with in the numerator, well, that's the same sort of multiplication thing that we just discussed. So the simplified form of this has no complex part in the denominator, which helps keep things a little simple and a little easier to interpret. Now in polar form, addition and subtraction, well, they're complicated. Under most circumstances, if you have two complex numbers given in polar form, it's easiest just to convert to rectangular form and add them together there. Multiplication and division, though, in polar form have very nice expressions. Q e to the I theta times R e to the I phi. Well, these are just all real numbers multiplying together, and then I can use the rules regarding multiplication of exponentials, meaning if I have two things like e to the I theta and e to the I phi, I can just add the exponents together. It's like taking x squared times x to the fourth and getting x to the sixth. But QR e to the I theta plus phi. So that was easy. We didn't have to do any distribution at all. The key fact here is that you add the angles together. In the case of division, it's also quite easy. You simply divide the radii, q over r, and instead of adding, you subtract the angles. So polar complex numbers expressed in polar form are much easier to manipulate in multiplication and division, while complex numbers represented in rectangular form are much easier to manipulate for addition and subtraction. Taking the magnitude of a complex number, usually we'll write that as something like z, if z is a complex number, just using the same notation for absolute value of a real number. Usually is expressed in terms of the complex conjugate. Now, the complex conjugate, notationally speaking, is usually written by whatever complex number you have, here in this case x plus iy, with a star after it. And what that signifies is you flip the sign on the complex part, on the imaginary part. X plus iy becomes x minus iy. The squared magnitude then, which is always going to be a real and positive number, this absolute value squared notation, is what you get for multiplying a number by its complex conjugate. And that's what we saw earlier with c plus id. Say I take the complex conjugate of c plus id and multiply it by c plus id. Well, the complex conjugate of c plus id is c minus id times c plus id. And doing the distribution, like we did when we calculated the denominator, when we were simplifying the division of complex numbers in rectangular form, just gave us c squared plus d squared. This should be suggestive if you have something like x plus iy, that's really messy, x plus iy, and I want to know the squared absolute magnitude. Thinking about this as a position in Cartesian space should make this formula, c squared plus d squared in this case, just make a little more sense. You can also, of course, write that in terms of real and imaginary parts. But let's do an example. If w is 3 plus 4i, and z is minus 1 plus 2i, first of all, let's find w plus z. Well, w plus z is 3 plus 4i plus minus 1 plus 2i. That's straightforward. If you can keep track of your terms, 3 minus 1 is going to be our real part, so that's 2. And 4i plus 2i, which is plus 6i, is going to be our complex part. Sorry, our imaginary part. Now, w times z, 3 plus 4i times minus 1 plus 2i. For this, we have to distribute, like usual. So from our top eyebrow terms here, we've got 3 times minus 1, which is minus 3, and 4i times 2i, both positive. So I have 4 times 2, which is 8, and I times I, which is minus 1, minus 8. Then, for my imaginary part, I guess the mouth and the chin, if you want to think about it that way, I have 4i times minus 1, minus 4 with the I out front, will just be minus 4 inside the parentheses here. And 3 times 2i is going to give me 6i plus 6 inside. The end result you get here is 8, or minus 8 minus 3 is minus 11, and minus 4 plus 6 is going to be 2. So I get minus 11 plus 2i for my multiplication here. I guess if I'm going to circle that answer, I should circle this answer as well. Now, slightly more complicatedly, w over z. W is 3 plus 4i, and z is minus 1 plus 2i. And you know when you want to simplify an expression like this, you multiply by the complex conjugate of the denominator divided by the complex conjugate of the denominator. So minus 1 minus 2i divided by minus 1 minus 2i. And if we continue the same sort of distribution, I'll do the numerator first. Same sort of multiplication we just did here, only the signs will be flipped a little bit. We'll end up with minus 3 plus 8 instead of minus 3 minus 8. And for the imaginary part, we'll end up with minus 4 minus 6 instead of minus 4 plus 6. And you can work out the details of that distribution on your own if you want. The denominator is not terribly complicated, since we know we're taking the absolute magnitude of a complex number by multiplying a complex number by its complex conjugate. We can just write this out as the square of the real part, 1, plus the square of the imaginary part, minus 2, which squared is 4. So if I continue this final step, this is going to be 5. This is going to be minus 10i, and our denominator here is just going to be 5. So in the end, what I'll end up with is going to be 1 minus 2i. So it actually ended up being pretty simple in this case. Now for the absolute magnitude of w, 3 plus 4i, you can think of this as w times w star square root. You can think of this as the square root of the real part of w plus the imaginary part of w. Sorry, square root of the squared of the real part plus the square of the imaginary part, which is perhaps a little easier to work with in this case, so you don't have to distribute out complex numbers in that way. Real part is 3, imaginary part is 4. So we end up with the square root of 3 squared plus 4 squared, which is 5. Now this was all in rectangular form. Let me move this stuff out of the way a little bit. And let's do it again, at least a subset of it, in polar form. In polar form, w, 3 plus 4i, we know the magnitude of w, that's 5. So that's going to be our radius, 5. And our e to the I theta, where theta is, like I said, the arctan. Since complex numbers are so important to quantum mechanics, let's do a few more examples. In this case, I'm going to demonstrate how to manipulate complex numbers in a more general way, not so much just doing examples with numbers. First example, simplify this expression. You have two complex numbers multiplied in the numerator, and then a division. First of all, the first thing to simplify is this multiplication. You have x plus iy times ic. This is pretty easy. It's a simple sort of distribution. We're going to have x times ic. That's going to be a complex part. So I'm going to write that down a little bit to the right, ixc. And then we're going to have iy times ic, which is going to be minus yc. That's going to be real. We also have a real part in the numerator from d here, so I'm going to write this as d minus yc plus ic. That's the result of multiplying this out. That's then going to be divided by f plus ig. Now, in order to simplify this, you have a complex number in the denominator. You know you need to multiply by the complex conjugate and divide by the complex conjugate. So f minus ig divided by f minus ig. Now, expanding this out is a little bit messier, but fundamentally you've seen this sort of thing before. You have real part, and imaginary part in the numerator. And then you're going to have imaginary part, real part and real part, imaginary part. And what you're going to end up with from this first term, you get f times d minus yc. From the second term, you have minus ig times ixc, which is going to give you xcg. We have a minus I times an I, which is going to give us a plus. Incidentally, if you're having trouble figuring out something like minus I times I, think about it in the geometric interpretation. This is I in the complex plane. This is minus I in the complex plane. So I have one angle going up, one angle going down. If I'm multiplying them together, I'm adding the angles together. So I essentially go up and back down, and I just end up with 1 equals I times minus I. Otherwise, you can keep track of I squareds equals minus 1s and just count up your minus signs. This, then, is the real part. Suppose I should write that in green, lest my fonts get too confusing. Excuse me. So that's the real part. The imaginary part, then, is what you get from these terms here. I'm going to write an I out front, and now we have xc times f, so xcf with an I from here, and then we have d minus yc times ig, which I'll just write as g d minus yc. In the denominator, we're now multiplying a number by its complex conjugate. You know what to do there. F squared plus g squared. This is just the magnitude of this complex number. Sorry, squared magnitude. Now, this doesn't necessarily look more simple than what we started with, but this is effectively fully simplified. You could further distribute this and distribute this, but it's not really going to help you very much. The thing to notice about this is that the denominator is purely real. We've also separated out the real part of the numerator and the imaginary part of the numerator. Yeesh. My handwriting is getting messier as I go. Imaginary part of the numerator. So we can look at this numerator now and say, this is the complex number, real part, imaginary part, and then it's just divided by this real number, which effectively is just a scaling. It's a relatively simple thing to do, to divide by a real number. As a second example, consider solving this equation for x. Now, this is the same expression that we had in the last problem, only now we're solving it for it equal to 0. So from the last page, I'm going to borrow that first simplification step we did, distributing this through. We had d minus yc for the real part, plus ixc for the imaginary part, and that was divided by f plus ig. If we're setting this equal to 0, the nice part about dealing with complex expressions like this is that 0, treated as a complex number, is 0 plus 0i. It has a real part and an imaginary part as well. It's just kind of trivial. And in order for this complex number to be equal to 0, the real part must be 0 and the imaginary part must be 0. So we can think of this as d minus yc plus ixc. This has to equal 0 and this has to equal 0 separately. So we effectively have two equations here, not just one, which is nice. We have d minus yc equals 0 and xc equals 0, which, unless c equals 0, just means x equals 0. That's the only way that this equation can hold, is if x equals 0. The key fact here is to keep in mind that in order for two complex numbers to be equal, both the real parts and the imaginary parts have to be equal. As a slightly more involved example, consider finding the cubed roots of 1. Now, you know 1 cubed is 1. That's a good place to start. We'll see that fall out of the algebra pretty quickly. What we're trying to do is solve the equation z cubed equals 1, which you can think of as x plus I y, where x and y are real numbers, cubed, equals 1. Now, if we expand out this cubic, you get x cubed plus 3x squared times iy plus 3x times iy squared plus iy cubed. And this is going to have to equal 1. Excuse me. Equal 1. Now, looking at these expressions, here we have an iy, here we have an iy squared. This is going to give me an I squared, which is going to be a minus sign. And here I have an iy cubed. This is going to give me an I cubed, which is going to be minus I. So I have two complex parts and two real parts. So I'm going to rewrite that. X cubed, and then now a minus sign from the I squared, 3xy squared, plus, pulling an I out front, the imaginary part then is going to come from this 3x squared y and this y cubed. So I've got a 3x squared y here, and then a minus y cubed, minus coming from the I squared. And this is also going to have to equal 1. Now, in order for this complex number to equal this complex number, both the real parts and the imaginary parts have to be equal. So let's write those two separate equations. X cubed minus 3xy squared equals the real part of, this is the real part of the left-hand side, has to equal the real part of the right-hand side, 1. And the imaginary part of the left-hand side, 3x squared y minus y cubed, has to equal the imaginary part of the right-hand side, 0. So those are our two equations. This one in particular is pretty easy to work with. We can simplify this. This is, we can factor a y out. This is y times 3x squared minus y squared equals 0. One possible solution then is going to come from this. You have a product like this is equal to 0. Either this is equal to 0 or this is equal to 0. And saying y equals to 0 is rather straightforward. So let's say y equals 0. And let's substitute that into this expression. That's going to give us x cubed equals 1, which might look a lot like the equation we started with, z cubed equals 1, but it's subtly different because z is a general complex number, whereas our assumption in starting the problem this way is that x is a purely real number. So a purely real number, which when cubed gives you 1, that means x equals 1. So x equals 1, y equals 0, that's one of our solutions. Z equals 1 plus 0i, or just z equals 1. Now, we could have told me that right off the bat, z cubed equals 1. Well, one possible solution is that z equals 1, since 1 cubed is 1. The other thing we can do here is we can say 3x squared minus y squared is equal to 0. This means that, I'll just cheat a little bit and simplify this, 3x squared equals y squared. Now I can substitute this this y squared, into this expression as well. And what you end up with is x cubed minus 3x, and then y squared was equal to 3x squared. So 3x squared is going to go in there. That has to equal 1. Now let's move up here. What does that leave us with? That says x cubed minus 9x cubed equals 1. So minus 8x cubed equals 1. This means x, again, being a purely real number, is equal to minus 1/2. Minus 1/2 times minus 1/2 times minus 1/2 times 8 times minus 1 is equal to 1. You can check that pretty easily. Now, where does that leave us? Where did I go? That leaves us substituting this back into this expression, which tells us that 3x squared equals y squared. X equals minus 1/2, so 3 minus 1/2 squared equals y squared, which tells you that y equals plus or minus the square root of 3/4 if you finish your solution. So now we have two solutions for y here coming from one value for x, and that gives us
our other two solutions to this cubic. We have a cubic equation we would expect there to be